Hey all, today we are going to start our fourth unit and we're going to start talking about making inferences. So far we've talked about displaying data, we've talked about collecting data, and now we're going to talk about what do we do after we've collected that data and made calculations. So I want you to take a second and read this bit about the Gallup poll conducted in May 2007. So basically Gallup was asking people if they believed in evolution. And what they found was that 43% of the people they polled did in fact believe that evolution was true. And then in another study, 41.9% agreed that evolution was true. Not the same percentage. So you might ask yourself, is it surprising that those two proportions were different? And the answer is no, and that's because there's always going to be variation when we're sampling. And you might also ask, so can you say that the true population is either 43 or 41.9? Again, the answer is no. In order to figure out what the true population of people who believe evolution is true, we'd have to survey everybody, which we talked about is not really possible. So I want to show you something in this applet. The Gallup poll said that they got 43% of their individuals who they surveyed said they believed that evolution was probably true or definitely true. And the way they calculated that was they just took the number of people who said yes, they think it's true, and divided by the 1,007 people they sampled. So I have this applet. I didn't make it. I'm borrowing it. And I put in here my 43%. So let's assume that that is the population proportion. I'm going to put my sample size that they took, 1,007. And then before I draw a sample, I want to show you what I can do on this graph down here. And I can actually lay the normal curve onto it. And so that's what the normal curve would look like, symmetric, unimodal. So I'm going to take that off. And let's draw one sample of 1,007 people. Now we could do this with a calculator. We could generate 1,007 random numbers, assign 43% of those numbers to be people who believe in evolution and 57% to people who don't believe in evolution, and that would be one sample, and we could count those 1,007 numbers and see what proportion of evolution believers we got. Of course, that sounds awful, and so let's use this applet, and that'll do it for us in the blink of an eye. And you can see it plotted a point here, close to 44%, and that is an example of one sample. So we can draw another sample, and another sample, and we can keep drawing samples and putting them on this graph. Okay, so doing these one at a time is sort of tedious. So I have now 30 samples. In the book, they decided, let's draw 2,000 samples. So I'm going to draw 2,000 more samples. And that would be, right now I have 2,030 samples. So that means I'm simulating randomly selecting 1,007 people and asking them if they believe in evolution. We did that 2,030 times. Using the computer program, we were just able to do that 2,030 times in the blink of an eye. And you should notice that it does look approximately symmetric and unimodal. And if I lay the normal curve over it, you can just barely see it. And I can keep drawing samples, and I have the normal curve back there. And you can see the more samples I draw, the closer it's going to get to being exactly the normal curve. And so that's a big deal. That distribution that we just made on that applet, it wasn't just one proportion, it was hundreds and hundreds and thousands of samples and the proportions we got there. And so we call that a distribution of proportions. And we're able to use a normal model because what happened here is always going to happen. If we take multiple samples and plot the proportions, they're always going to end up being approximately normal. And so with that, when we have a normal model, we always need to know the mean and the standard deviation. So remember, mu is mean. P hat represents a proportion from a sample, and P represents the population proportion. So if you look on this applet, they have the Greek letter pi here, and that would be sort of like what we would use if we were following suit with our Greek letters for population proportions, but we already have an understanding of what pi means, so we'll use P, and then we'll use P hat for a sample. SD here just means standard deviation. Q is the same as 1 minus P. So P being our mean of a sampling distribution model for proportions, Q being 1 minus that mean, and then this being our standard deviation. So in our example, our mean was 43%, Q was 0.57, and our standard deviation was 0.0156. So we take P and Q and multiply them and divide by our sample size. So we would have a normal unimodal symmetric curve centered around 43% with a standard deviation of 0.0156. In order to use the normal model, we do need to meet some conditions and assumptions, or else it won't follow the normal model. We always have to have a random sample or a randomized experiment being done in order to collect this data. We need our individuals to be independent of each other. Sometimes it's not possible to know if they're independent of each other, but if you sample 10% or less of the population, then we can assume that those individuals are independent. So we have to meet this independence assumption. And we also have to meet a normal condition, or what we call a success failure condition. So NP is the number of samples times P our proportion, N times Q. Those two values need to be greater than or equal to 10, meaning we need to expect at least 10 successes in our sample and at least 10 failures. So let's look at our evolution. And we would expect at least 433 people to believe in evolution and at least 573.99 to not, and so those are both greater than 10. Also, 1,007 people is far less than 10% of the American population, and they did claim that they did a random sample. So in our original example, we've met all the assumptions and conditions. So I want to do an example with you. Take a second and read this here, and then we'll discuss how we can use this knowledge of the sampling distribution to answer the question. So we're talking about BMI about female college students. And the first thing we need to do before we start using a normal model would be to meet some assumptions and conditions. And so they selected randomly 200 students, so we meet the randomization condition. 200 students is definitely less than 10% of all females at a large college, and so we've met the independence or 10% condition. And then we can calculate NP and NQ. N is our 200 students. P is the 22% that the CDC claims of 18-year-old females who have a BMI of 25 or more. Q is 1 minus that, so 0.78. We could plug those values into NP and NQ, and we can see we expect at least 44 successes and 156 failures, and so we're greater than or equal to 10. We've met all the assumptions and conditions. We can go ahead and assume that a normal model would fit this sampling distribution. And the sampling distribution would be of if we were to keep randomly selecting 200 female students, reporting their heights and weights, and calculating their BMIs, and getting the proportion of students who had a BMI greater than 25. So we have some notation here I think we talked about earlier this year. We're using a normal model with mean P and standard deviation square root of PQ over N. We can plug in what we know. This P comes from what the CDC says the population proportion is. Same thing over here. 200 is our sample. So we have a normal model for the sampling distribution of the proportion of female students with a BMI over 25 that has a mean of 0.22 and a standard deviation of 0.029. Our p hat, our actual sample proportion, was the 31 students who had a BMI over 25 divided by the 200 they sampled. And so the question here is this sample unusual? And so when we talked about being unusual earlier in the year, we calculated a z-score using this formula. Well, we need to massage this a little bit because now we're talking about proportions. And so it looks something like this. P hat minus P over our standard deviation of our sampling model. We can plug in what we know, and we get a z of negative 2.24. So we discussed earlier that anything greater than 2 standard deviations above or below the mean is going to be considered unusual. And so, yeah, we can say that that sample that they found was unusually small because it's more than 2 standard deviations below the mean. So take a second here, read this one, and we'll do one more example. So here we're talking about left-handed desks in an auditorium. Before we can find a probability, let's see if we meet the conditions. Typically, students are randomly assigned to classes, so we can say that the randomization conditions met. 90 students would be less than 10% of all students at a school. And we can calculate NP and NQ. N is our 90 students in the class. 0.13 comes from the 13% of the population that is left-handed. And we meet our success failure, our normal condition. So we'll then approximate our sampling distribution of the proportion of students who are left-handed using a normal model. Our mean is that 0.13 that we said 13% of the population is left-handed. And so we have a normal model with a mean of 0.13 and a standard deviation of 0.035. In order to calculate a probability, we need to find a z-score. And so we need our p hat. We're looking to see if we're going to have possibly more than 15 students who are left-handed because there's 15 lefties in this auditorium. So our p hat is going to be 15 out of 90. And we'll calculate a z of 1.06 by plugging in our p hat, and our standard deviation. So this is where we would take our z and we would plug into the calculator for normal CDF. And we have a very important notation here. We're looking to see what the probability of having more than 15 left-handed students would be. So that's a right tail. And here's how we write a probability. The probability of our sample proportion being greater than 0.167, that's 15 out of over 90, which is the same as the probability of our z-value being greater than 1.06. And when you plug into the calculator, if you don't have a calculator, that's fine, we get an answer of 0.1446. So there's about a 14.5% chance that we'll take 90 students into this auditorium and we won't have enough left-handed seats for the class. So I have a few questions today for you to answer in regard to this problem. So make sure you watch till the end and you answer all the questions. Make sure if you have questions about this lesson, you ask me when we're together, and I'll be happy to work through it with you.